So in this section, we are going to talk about the logistic equation. And the logistic equation is actually a way to better model population and to model something like the spread of disease. And logistic equations are really quite interesting because they look something like this, have like an S shape to them. And they're one of the types of equations that actually have two horizontal asymptotes. We're going to have a horizontal asymptote here at y equals 0. And then we're going to have another one here at what's called the carrying capacity. And when we have a logistic equation, it's going to be similar to this model. C is the carrying capacity for this model. And the carrying capacity is the maximum number of people or the maximum number of items that we could possibly reach. So it's what's happening as time goes to infinity here. Where is this heading? So if you think about something like the spread of disease, well, if we're talking about like a global spread, whether it's the flu or COVID or whatnot, the maximum number of people that could be infected would be, well, for us, it would be everyone on Earth. If we're talking about maybe a secluded tiny island somewhere where people stay on that island, the maximum number of people would be the maximum number of people that would be on that island, and that would be the carrying capacity. We can think about carrying capacity in terms of population. Let's say we have a farm that has a set acreage, and we have so many cows or bunny rabbits. We can't hold an infinite number of bunny rabbits on our farm because we only have so much room for them to spread out. We don't have an infinite area there. So the carrying capacity would be the amount that we could carry there. So that population model would resemble something like this, where we have a maximum that we could reach because we only have so many resources in that situation to give to the population of rabbits. So I want to talk a little bit more about where this equation is coming from. I want to derive it from the differential equation, and then we're going to go back and analyze the logistic model a little bit more. So let's start with that differential equation. The differential equation for a logistic model is dy over dt is equal to ky times 1 minus y over L, where L is the carrying capacity. So K is your constant of proportionality there. We can solve this by separating the variables. So our first step would be to multiply both sides by dt and then divide both sides by y times 1 minus y over L. So that will separate our variables. So I don't like to deal with complex fractions, so we're going to simplify that complex fraction. So we have 1 over y times 1 minus y over L. That's equivalent to, in the denominator, y times L minus y over L. And if we think about that keep, change, flip, we're going to have L over y times L minus y. So integrating the right-hand side is easy. That's just going to be kt plus the constant of integration, which I'm going to choose to put on the right-hand side. The left-hand side is going to involve partial fraction decomposition. So let's do that on the side over here. We have L over y times L minus y. And we have non-repeated linear terms. So our setup's going to be a over y plus b over L minus y. So L has to be equal to a times L minus y plus b times y. So if we build that system, let's look at the coefficient of y. On the left it's 0. On the right it's negative a plus b. And then if we look at the constants, on the left we have L. On the right we have a times L. So this tells us, if we divide both sides by L, that a has to be equal to 1. And now that we know that a value, we can substitute in to find b. And we see that b is going to be 1 also. So that left-hand side we could write as 1 over y plus 1 over L minus y. So then if we integrate, we're going to have the ln of the absolute value of y. This is going to be a u substitution. We're missing the negative 1. Compensate with a negative outside. So that's going to give us a negative ln of L minus y equals kt plus c. Combine the logarithms on the left. And I'm going to rewrite this as an exponential function. So I have e to the kt plus c, which is just going to be c1 e to the kt, is equal to y over L minus y. Now let's solve this for y. We can do that by multiplying both sides by L minus y. So I have c1 e to the kt times L minus y is equal to y. So I have c1 times L e to the kt minus c1 e to the kt times y is equal to y. We can move the y terms to the right-hand side. And then factor a y out. So we have c1 e to the kt times L over 1 plus c1 e to the kt. And that's equal to y. So that's not quite what our logistic model looked like a minute ago. So let's do some tweaking here. Let's multiply the top and the bottom by 1 over c1 e to the kt. That way it eliminates that exponential in the numerator. So when I do that, I'm going to end up with just L on the top. There's our limiting or carrying capacity there. And I'm going to have 1 over c1 e to the kt plus 1 in the bottom. And that's equal to y. So then we could rewrite that as 1 over c1 times e to the negative kt plus 1. And this is just another constant. I'm going to call it b. And usually logistic models are written in the denominator 1 plus b e to the negative kt. So there's our logistic model that we were talking about just a minute ago. Just using different variables here and here. So now that we have that logistic model, I want to do some fun stuff with it. Like we said before, that number that's on top when it's written in this form is the carrying capacity. That's the maximum number that can happen. That will be a horizontal asymptote for this particular problem as well. So we could think about that carrying capacity in terms of a limit. If we were to take the limit as t goes to infinity, what happens to this? Well, what's going to happen is that we're going to approach that horizontal asymptote, that carrying capacity of y equals 0. If you think back to Calc 1, that's actually how you found horizontal asymptotes. We're taking the limit as x goes to infinity and as x goes to negative infinity. We wouldn't go to negative infinity in this case because we're talking about time, and time's not going to be a negative. So there's your models. If we are talking about logistic growth, like if we're talking about spread of disease, it's going to be modeled this way, where we're talking about how many people are infected or have been infected with a certain disease. Our COVID models would be modeled just like this. Flu models would be modeled like this, and so on. If we have a logistic decay, it's going to look like this. So slightly different model. Just depends on what that B rate is, which is that value in the exponent, whether it's positive or negative. So what are some properties? The domain is going to be the set of all real numbers. If we're talking about real life examples, we're talking about time. So usually we talk about the starting point at time 0, and then we go up to infinity. So we don't really think about negative time values there. Just depends on the problem. But real life, you go from 0 to infinity. The range is going to be from 0 to the carrying capacity. Notice there's not any x-intercepts, but there's going to be a y-intercept, and that's going to be at time 0. We do have two horizontal asymptotes. One is the x-axis, and the other one is y equals c, where c is carrying capacity. There is an inflection point on this graph. That inflection point happens at half that carrying capacity, and you could prove that using Calc 1 techniques. That's where the graph changes from being concave up to being concave down. So we have this increase here, and then we change, and it starts to level off, if you will, past that inflection point. It's growing pretty rapidly in here. The graph is also a smooth, continuous graph with no corners or cusp, which means that we can deal with differential equations and talk about differentiability of the function. So let's look at an example here. Let's look at the fruit fly population. Fruit flies are placed in a half pint of milk with a banana. And we have a population model. They've given it to us. They're asking us some questions about that model. First question is asking, what is the carrying capacity and what's the growth rate? So if we look at this, the carrying capacity is going to be 230. So I'm going to use C for carrying capacity. And then our growth rate is going to be that 0.37. So this one's growing. If you go back over here to look at that model, notice this exponent down here is going to be negative. As long as B is positive, it's always going to be a negative here, which means we have a growth. So we're increasing that population in this case. B's asking, what is the initial population? Well, that's going to happen at time 0. So we need to plug a 0 into this. If we plug a 0 in for that time t, we're going to have 230 divided by 1 plus 56.5 times e to the 0. And e to the 0 is 1. So we're going to have 230 divided by 57.5. Which is 4. So we started out with a population of 4. They're asking us in part C, what's the population after 5 days? So we're going to plug a 5 in here. And we could graph this. We could put it in our calculator and then use the table feature to find that population. You may want to take a moment and do that. So if I plug 5 in for that t value, I ended up with 23.27. I'm going to round that down to 23. Its population was 23 flies at that point. D's asking us how long is it going to take to reach 180. So we can solve that algebraically. 180 is equal to 230 over 1 plus 56.5 e to the negative 0.37t. Multiply both sides by the denominator. Let's divide by 180. 230 divided by 180 is 23 over 18. Subtract 1. Subtract 1, I'm going to get 5 over 18. We could divide by 56.5. So we have 5 over 18 times 1 over 56.5. Take the ln of both sides. And then divide by negative 0.37. I saved all the computations for last. So I got about 14.4 days. So in a little less than 14 and a half days, we will have 180 fruit flies. So then E's asking us how long is it going to take for the population to reach 1/2 of the carrying capacity. The carrying capacity here is 230. Half of 230 is 115. So we need to set 115 equal to 230 over 1 plus 56.5 e to the negative 0.37t. So we could do this algebraically just like we did a minute ago. We could also do it in the calculator. So I'm just going to plug it into the calculator. So here's my logistic model. I'm putting that in for Y1. I'm going to put the half the carrying capacity. That's where the inflection point is going to be, which was 115 in for Y2. And I'm looking for the intersection. So I'm going to have to do some tweaking, I think, to change my window. So we know after 14 and a half days, the population was 180. We know that from the previous part. So we need to go past 14.4 because we want to reach, actually, we don't even have to go past 14.4. I do want to see the whole graph though. So I'm going to go a little bit past that. Let me use 20 for my X max. I'm going to go up by 2s. My Y max, we know the carrying capacity is 230. So we're starting to see that model curve in here. If I go just a hair more to the right, just so we can see it a little bit better, you're seeing that classic S curve with that. And we're trying to find the intersection. So we can hit second. And then trace. That's our calculate menu. Go down to intersect. It's going to ask you for a first curve, second curve, guess. So it looks like about 10.9 days we will be at 115. So T is going to be equal to 10.9. So we could do the same kind of thing for the next problem. We have some bald eagles that have been set free somewhere in Montana, and we have a logistic model that will model that population growth. They're asking us some questions. So let's start with the carrying capacity. And before we answer these, you may want to pause the video, try these yourself, and then come back and check your answers. So for this one, the carrying capacity is 500. That's our C value. The growth rate is right here at 16.2%. We can graph this in the calculator, and then we can find the answers for the rest of the problems. So I'm going to do that. So there's my graph based on the previous window. Let's change our window. We know our carrying capacity is 500. So I'm going to change my Y max to 500. And I'm not sure how far to go out here, so I'm just going to make a guess. Let's go maybe 80 units out and see where that puts us. Alright, so it seems like that works pretty well. So there's our nice S-curve. There's our logistic model. D is asking us what's the population after 3 years. So we just want to plug a 3 in for that T value, and we can do that in the calculator. Now, I do have my hit second window. I have my table set independent to ask. That allows me to type in any X value, and it will give me the Y value. Keep your dependent on auto. So hit second and Y equals. And I'm going to type in 3. So after 3 years, we have approximately 10 bald eagles. Now they're asking, when is the population going to be 300? We could solve it algebraically. Or we could just say, when is that equation equal to 300? And find the intersection. It's going to ask us for a first curve, a second curve, and then a guess. So that happens about 29.7 years in. And then it's asking us, how long is it going to take to reach half of the carrying capacity? So that's that inflection point again. Lots of ways we could do it. We could set the equation equal to 250, which is half of the carrying capacity. We could use Calc 2 techniques. Or we could use technology. I'm going to use technology. So we're going to set this equal to 250 and find the intersection. So that intersection is happening at 27.2. So it's going to take a little over 27 years to reach that half of that carrying capacity for this population. So there's our answers for this problem. Now, you may ask where these types of models come from. What happens is data is collected over a period of time, and they find that best fit logistic model to come up with this type of equation. So we could do it that way. If we know something about the growth rates, we may be able to come up with that differential equation. And then do some integration to come up with it also. So there's a couple techniques that could be used to find that model. So let's look at another one. We have a state game commission that releases 40 elks into a game refuge. After 5 years, the elk population is 104. The commission believes that the environment can support no more than 4,000 elks. And we have the growth rate elk of the population in terms of a differential equation. They're asking us to write a model for the elk population in terms of T. So in other words, solve that differential equation and solve it for P. So if we wanted to do that, we could integrate, and then we could use our conditions to figure out what our constants are going to be. So we already know some information here. We know that the carrying capacity is 4,000. We know that at time 0, 40 elk were released. And we know 5 years later, there were 104. So if we take this model and we integrate it, we will end up with our equation here. And it's going to be 4,000 over 1 plus BE to the negative KT. So how do I know that? Well, we did the derivation a little bit ago, and so that's kind of the heavy lifting for this problem. So there's our basic equation we started with. Notice that L is in the denominator. If we compare that to the equation they just gave us, and I'll write it here, we have dP over dt is equal to Kp times 1 minus P over 4,000. We know that this model will give us this differential equation. So that means we should be able to translate this into something like that. And we know our L value is 4,000. They gave it to us in 2 places. They told us the limiting capacity, and then they gave it to us in that differential equation, which was that denominator there. So we could go through, do the integration and show that, or we can use what we've already previously derived to solve that. So I'm going to use that previous derivation. So now we've just got to figure out what our B value is going to be and then what our K value is going to be. And that's where those initial conditions are going to come into play. So we know that at time 0, we had a population of 40. So 40 is equal to 4,000 over 1 plus B. So 40 times 1 plus B is equal to 4,000. 1 plus B is equal to 4,000 divided by 40, which is 100. So that means B is equal to 99. So now we know that population is 4,000 divided by 1 plus 99, e to the negative KT. And this is where we're going to use that second condition. We had a population of 104. And that was 5 years in. So we have 4,000 divided by 104, subtract 1. divided by 99. Take the ln of both sides. And then divide. And I am going to round this. I'm going to use 6 decimal places, though. That way our final answer is accurate to about 3. So, our model is this. B is asking us to graph the slope field for the differential equation and the solution that passes through the point. So we could graph that in Desmos, and you would see how this matches up. I encourage you to do that on your own. C is asking you to use the model to estimate the population after 15 years. So if we were to plug 15 in there, what would be our estimated population? I'm going to use a calculator to do that. And when I plug that in, I got about 628 elk. And then D is asking for the really the carrying capacity. What's happening as T goes to infinity? Well, as T goes to infinity, this term is getting smaller and smaller. So remember what that really means with that negative exponent. I'm going to rewrite this. So that's really 99 over e to the positive 0.1943661t. So as t gets bigger and bigger, that denominator is getting bigger and bigger, which means that entire fraction is approaching 0. So this is approaching 4,000 over 1 plus 0, which is approaching 4,000, which is that carrying capacity, which is also the horizontal asymptote for that particular problem.